Welcome all to this 21st lecture of Principles of Statistics. Today, we're going to talk a bit more about the bootstrap and inferential procedures in general. And, the bootstrap is some sort of sampling procedure. And so then after that, we'll start a new section that will be on sampling procedures, and in particular about Monte Carlo sampling procedures. Okay, so let me then sort of go back a bit in conceptually and say that, implicitly, what we have seen during the course and what you have seen from Stats 1B and just in general in stats is that, one of the most useful ways to derive inferential procedures is as follows. Inference or inferential is using so-called pivots, okay? Pivots or roots as well. Okay. So what is a pivot? Well, this is a function of the data and possibly of the unknowns too. But that is very special because even though it may depend on the unknowns, its distribution does not depend on the unknowns. Yeah? Okay, so for instance, just to clarify this, let assume that we have a sample x1 to xn from a normal distribution with mean mu and variance, so univariate sigma squared for some mu in our sigma squared positive unknown. Yeah? Unknown. Yeah. Then the ratio of the sample mean minus mu divided by sigma is precisely distributed according to a normal or a standard normal distribution, and so this is a pivot. Yeah. Okay. All right, that should be clear, the concept. So I guess the other thing to say is that pivots, maybe, so this is a bit maybe too ambitious to have, these guys having exactly, or knowing exactly the distribution and therefore knowing that whether, it depends or not on the unknowns. But what we have from the asymptotic normality of the MLE, for instance, is that we know that some quantities can be asymptotically pivots. Yeah. Okay. So let's say that, or let's state that. So in many occasions, okay, so now that we have a pivot, we may use it, but in many occasions it may happen that because it depends on the unknowns, we cannot use it directly, right? And we need to substitute some of the unknowns by some some estimators or something like this. Yeah. So let's say this. So in many occasions, I guess. Okay. So let's say when the pivot depends on the unknowns, we cannot use it directly. Yeah? And we require some sort of proxy. Okay, so for instance, in the case above, we can take, xn minus mu divided by Sn, where Sn is, or the square of it, is this n plus 1, and then sum from 1 to n of the xi minus the xn. Yeah. Okay, squared. Yeah. Or could also, yeah. Okay, so that's one thing. Yeah. So we've seen this in how to construct confidence regions, for instance. Yeah. Okay. So. Okay, and these are still. This is still a pivot. Yeah. Okay. So. So in practice, well, maybe not in practice, but in most cases, I mean, looking for quantities that have exactly a distribution that we know and which doesn't depend on the parameters may be a bit too ambitious, right? So instead, what we can do is to use this asymptotic, well, for instance, when we're using asymptotic normality of MLE, what we have in mind is that the quantities we're going to use are not pivots, but they are asymptotically pivots. Yeah? So this is what we're going to sort of mention now, because that's really what matters. In practice, this is what we encounter. Yeah. Okay. So in most occasions, we use asymptotic pivots. And I think it should be clear, right? So the difference with the pivot. So this is a quantity that depends on the data, and that may depend on the unknowns, but whose distribution or asymptotic distribution will be independent of the unknowns. Yeah. Okay. And then, we also need, again, a proxy for it. For them. Yeah. So, and now what we see precisely is that the bootstrap is one way of constructing these, right? So the bootstrap is a recipe to construct such proxies. Okay. What we have is that we have two types of bootstrap. Yeah. So, and in the context of parametric models, we have two types. So-called parametric bootstrap and non-parametric. So you may be surprised, but actually what we've been talking about so far is non-parametric, yeah? Even though we are sort of sticking to parametric models. So yeah, so we have seen the latter, and we were so far restricting to the estimation of a mean. So in the context of confidence sets for the mean, okay, so this is what we've seen, but things are much more general than that. And so just to remind you, what we do here is just that, so we compute, we have a sample, so we have, let's say, okay, so sample x1 to xn, okay, and also the xn1 bootstrap to xnn bootstrap. And then we compute also so we compute the MLE. It's going to be given by this, and this guy is no more than, well, as in this is a function of these guys. And we're also going to compute a similar quantity that is going to be, yeah, okay, so these guys of course follow from, as in these guys are from that distribution, yeah, that's clear. And then I guess I just wanted to make that very, very clear. Okay, so we compute these and this, yeah. So then, what do we have? Well, we have that, we have a proxy, right? So then square root of n of this theta n hat with b, so the bootstrap one, minus this one is a proxy. It's a proxy for the asymptotic pivot given by this, okay? So we're talking about a model that has, that is indexed by theta, and theta is the mean, and then you have this, yeah? So then, okay, so we have this proxy, and because we're in the context of confidence sets for the mean, then we can compute Rn such that the probability under this sampling or resampling distribution of the difference, well, or of the pivot essentially up to this square root of n, we want this to be 1 minus alpha, yeah, for some alpha, as usual. Okay, so we can do this. And then once we do this, we can set, if we want to get this confidence set, we set CNB to be the set of thetas such that, so this is just the same thing that we did before, but rather than using knowledge of some asymptotic distribution, we just use this empirical distribution, yeah? Okay. Okay, so let's note the following, and that is that we haven't really used these asymptotic, well, not even asymptotic. So we haven't really used the model so far beyond saying that it is indexed by this theta, yeah, and that the theta is the mean. So in parametric bootstrap, we'll exploit precisely this statistical model that we are assuming. Yeah, so that's the difference between them. Yeah? Okay, so let me just say that. So have not used the statistical model or the underlying statistical model beyond saying it is indexed or parameterized. Yeah, maybe better, parameterized by theta. Okay. So in parametric bootstrap, we're going to exploit this. Yeah? This additional info. Okay. So it basically proceeds exactly in the same way, but the only difference is that is the way in which we're going to sample these bootstrap samples. Yeah, so it proceeds as above, except for the fact that you know, these guys, the xn1, b, and so on, you know, rather than being distributed according to the pn, they are IID according to the p. So this is the distribution of the in the model, and we plug in the MLE. Remember, the MLE has to belong to the parameter space, so we can, you know, it's fair to just take the distribution from the statistical model that or whose parameter is exactly this MLE. Yeah? Okay, and so let's just sort of, because this was a bit more like a remark, I guess, and so let's I guess carry on with the remarks. So let's say remark. Okay, so neither requires knowledge of the asymptotic distributions. Okay, of the I guess of the pivot, or of the asymptotic pivot. Okay. Pivot. Or of the Fisher info. Yeah? Even less so, right? Okay, so okay, but we still have if the statistical model is regular, then it still holds for both of these procedures that the probability when the theta naught is the true parameter of the true parameter being in these guys, and this is just, this can be for the non-parametric and also for the parametric, one is going to go to, it's going to convert to 1 minus alpha, yeah, for both. Both procedures, yeah. Okay, so that's one thing. Then the second, which I was close to talking about before, is simply saying that, well, because we didn't exploit the underlying statistical model in the non-parametric bootstrap, then actually non-parametric bootstrap is, can be used much more generally, right? So, okay, so I guess from the explanations above, it's clear, that so non-parametric bootstrap resamples so directly from the from the sample. So it applies, or it can be used. In more general contexts than parametric models. Whilst parametric bootstrap so parametric bootstrap will be will use the underlying statistical model explicitly prior to resampling or for the resampling. So when the statistical model is correct, so this is, a very particular case, it will perform no worse than non-parametric bootstrap, yeah? So, I mean, what I'm saying is something very evident, yeah, or very intuitive, and is that, non-parametric bootstrap can be used in much more general contexts, but if we restrict ourselves to the very specific context in which we correctly specified the model, then using, exploiting that extra information is going to be beneficial, or at least it cannot hurt us. Yeah. Okay. Okay. So let's say then. Okay. So we're done with bootstrap, and let us now talk about sampling methods. And the ones we're going to consider are the so-called Monte Carlo and this I will shorten by MC, so Monte Carlo methods. Okay, so I guess let's make a remark, and it's that so far we've always been talking about having asymptotic distributions, or posterior distribution, or an empirical distribution, and we want to compute things about them, right? So we want to compute an expectation, for instance, or we want to compute quantile, and so on. Yeah. So the issue is that generally it's not so easy to sample from distributions, right? At least, think of the easiest cases. The easiest example is the posterior distributions. Yeah? So posterior distributions can be very complicated, and so it may not be easy at all or possible at all to sample from them sort of directly. As in that there is no closed form necessarily for them, and even if there is, it may not be it may not be very simple. Yeah? Okay, so let me say that. So any previous inferential procedures require knowledge of various aspects of asymptotic, sort of posterior, empirical distributions. Yeah? So this is what we've seen, such as expectations or quantiles and so on. Yeah. So let me just say this like this. So for difficult distributions, and by difficult, I can mean, posterior that is just very involved, but I could also mean, something that is very high dimensional, and then, that we have some difficulties in there inherent to this high dimension, that is not necessarily a very, very complicated distribution, but there are issues with high dimensions. So for very difficult or for difficult distributions, we generally have to approximate these, and we will generally do it via sampling. Yeah. From precisely the underlying distribution. Okay, so is there any way in which we can sample from a general distribution? Well, yes, there is a general recipe. So let me give it to you, and you will see it in the example sheet, which, by the way, I've taken down the fourth one, because I want to add, a question or two. So bear with me, please, and I will upload it this week. Okay, so let F be a PDF. Sorry, a CDF. Cumulative distribution function. Okay, and we're going to define its generalized inverse. Function by the following, or as follows: F minus at U is going to be the infimum of the real numbers that whose image through F is greater than or equal to U. Yeah. Okay. So then what we see, or what you will prove in the example sheet, is that if U is a uniform distribution on 0-1 interval, then x equal to this f minus 1 u will be distributed according to f. Yeah? Okay, so that's yeah, so that's a very sort of useful result, or at least in some cases. So because then if we can sample so hence if we can sample U1 UN IID according to a uniform 0-1, then we will get, so we can sample x1 star, xn star according to, so we can sample a sample from F, yeah? And importantly, by the law of large numbers, strong or weak, I don't mind, we can approximate a general expectations. Yeah? Just as follows. So what we have is that the expectation under F of some G, some general G, is going to be approximately. Well, let me maybe say general expectations. Okay, so let's say this. Okay. Where G, is a function from R to R, measurable, of course. Any such function. So we can approximate general expectations by the so-called Monte Carlo approximations. Okay, and in this case, this is given by simply 1 over n. From 1 to capital N of G X I star. Yeah. Okay. And actually, so let me say, I want to make a difference between, I want a difference between the small n that we had before and the large n that we have now. Because the small n is the sample size for a sample that we've sort of given, yeah? And I wish to have capital N to denote something that we have control over, yeah? Which is the number of samples that we can simulate, yeah? Number of, or elements in the sample that we can simulate, yeah? Okay, so, okay, so then can we simulate these uniforms? That's the question, right? Well, let's become a bit practical, yeah, and say that any task performed by a computer and a current one, I don't know what will happen in the future, computer is ultimately based on combinations of zeros and ones, right? zeros and ones. Yeah? So, if we wish to be able to sample the U's, then we need to do it through zeros and ones. Yeah. So can sample this, well, let's say U, let's start with just one, right? Using dyadic expansions, yeah? Okay, so a fact is as follows. So fact, we have that. So U given by the sum, the infinite sum this kind follows a uniform distribution on 0, 1, if and only if, okay? So if and only if the epsilon i's are IID Bernoulli random variables, yeah? Symmetric Bernoulli. Yeah, okay. So we have a recipe basically, but now of course another issue in practice is that computers never gonna be able to these infinitely many operations, yeah, but that's not necessarily too bad in this case. So computers so let's just say, so computers have finite precision, right? So what we are really left with in practice is that we only have to sample finitely many of these guys. Yeah. I guess finite lists, or finitely many zeros and ones, but we have to do it in a particular way, right? Because we need to we wish to to do so in this IID way, right? Which is not actually, at least with current computers, so with with sort of quantum techniques, one can get real randomness, but with real current computers, it's not really, you cannot attain randomness. So you have to have something that is that looks like in some way, yeah. The epsilons or in such a way that they look, and I don't want to go into details of what this means, they look IID, yeah, so the zeros and ones, yeah. Okay, so this is what is called, this is the theory or the practice of pseudo random I guess, number generators. And if you want to learn more about this, then you could see the book by Robert Casella. Okay, that is called precisely Monte Carlo statistical techniques. Yeah? Actually, methods. Yeah. Okay, so again, this is a general recipe. So general recipe. But many times what we have is that this F minus, or okay, so let's say the computing this F minus is inconvenient or directly unfeasible. Okay, so think of the example in which the standard normal directly, yeah. Okay, so I'm talking about. So maybe it's better if I just say so. Okay. Okay, so we have some alternatives here. So we can either, use or I guess exploit some specific structure. So use specific transformations of uniform distributions random variables okay, so see example sheet for this standard normal case, or or we can find other recipes, yeah. Or we can have other generally less efficient. I say generally because, of course, if you cannot, if it can be very costly to get this inverse function. So maybe that actually that doesn't compensate. So less efficient general recipes are available. Okay. So these, generally speaking, will try to give you samples from the desired distribution, but it may be that they just directly estimate the aspect of interest. So let me then, so both for sampling or directly estimating aspect of interest. Okay, so we start with one of the latter sort of type. This is what is called importance sampling. Yes. Okay, so what do we get in here? So we're going to estimate directly an expectation. Okay, so let's assume F has PDF small f, okay, that we can evaluate. As in, it's not only a theoretical construct, but rather this is something that is tractable in some sense. Okay, and also assume that we can sample from PDF, so from a different PDF h. Yeah, and we're going to get, and we're going to assume, sorry, that this is positive everywhere, just for simplicity. Yeah. And in fact, it's nearly necessary. Okay, so then let us call the samples from this H, the usual thing, but with the star. So assume these are IID. According to H, then we have that this expectation of interest that we had, okay, we can write it as, so this would generally be, GF, essentially, so the integral of these two, but let us now write it a bit differently. So let's write GX and FX, it would have been right, but now let us multiply and divide by HX and multiply by HX. And then what we see is that this is now, the PDF, and so this can be approximated by 1 over n. Okay, so not enough space. So we can now approximate this by 1 over n of the sum from 1 to capital N of GXI star, FXI star, HXI star, right? Okay, so what we see is that, before we would have had just a G with XI rather than X star, if you like, because the X would have come from the capital F, but now it comes from the small h. But it's essentially the same sum with now some weights, yeah. So importance weights, yeah. Okay, so these are importance weights, so-called importance weights. Okay, and this gives the name to the importance sampling. Yeah. Okay, but let me mention something about this procedure, because in or this importance sampling can also be used when we want to compute this expectation and we are happy with this Monte Carlo, but actually we want to reduce the variance. So it can also be used to reduce variance of the Monte Carlo approximation to this expectation. Yeah? Okay, so note that the variance under, or the variance just simply of this guy that we have, that we were looking at, this is under H really, is no more than 1 over n of variance of GF divided by H. Okay, so this means that so choosing H, sort of proportional or approximately proportional to this, approximately, will generally reduce or improve upon, let's say, upon just simply, not introducing anything. So H equal F. Yeah. And why this choice, this guy here? Well, that should be sort of clear, right? So if we were, exactly proportional to that, then we would have two constants depending on, this random variable would only take two values, and so it would have very little variance, yeah, compared to, for instance, this choice. Yeah. Okay. So now let's Okay, so I'll stop here for today, and we'll go into the second type of methods in the next lecture. So these are going to be sort of sampling methods that you sample directly from the distribution of interest. Yeah. Okay. Well, I hope you enjoyed the lecture and hope to see you soon in the next one. We're nearly done.